Good afternoon, year 13s. Thanks for coming, guys. Sorry it's taken me so long to get this all ready. So I'm just waiting for my YouTube channel to start streaming. It takes about 30 seconds or so. And then I pause.
Sorry it's taken me so long.
There we go. Wink it. Hi, question mark. I know it takes a while. Sorry about this. Pop out chat. Then I can shut down my YouTube video there and keep that up. I like it. Get rid of that bit. Winkit. Hi, Winkit. Hi, Julian. Oh, my goodness. What are you guys like? Right. Okay, guys. So we're starting a brand new topic today. So we're looking at transition metals under aqueous conditions. This is the reactions. This is the reactions of transition metal compounds when in water. So we've got a whole sequence of lessons to go through. One, we need to talk about the acidity of transition metals in water. I'm wondering what learning objectives. Oh, that's interesting. Hang on one sec. There we go. Let's find my notes. Nope, wrong one. There we go. The metals to learn is the right thing. I like it. Right. What I'm going to do, I'm going to share my screen with you guys. Share screen. And we can kick off. Let's go for that one. There we go. Fab. Right. Okay, guys. Straight into here. Okay. So, aqueous chemistry, lesson 1. So, 3 learning objectives today. Number 1, know the metals to learn. Now, guys, there's a whole load of things here. Number 1, you've got about 50 colors to learn, and there's a lot. And as I said, I've mentioned this in previous lessons, you do not learn them individually. What you do is you learn them in groups. So, for example, chromium, purple, green, 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 purple, green, but it's not purple at the beginning, it's violet. You learn it in a string. Cobalt, pink, blue, 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 straw, yellow, pink. Yep, you learn these in strings to make it a little bit easier. But I want you to first of all have the list of all the metals you're expected to know about. So let's list them. Oh, before we do that, so let's just put a little bit of a definition of what aqueous chemistry is. I'm going to put transition metal. I'm going to shrink my pen here. No, I'm going to stick with that. Transition metal, aqueous chemistry. The study of properties and reactions, the study of properties and reactions of transition metal compounds in water. That's the one. So we've done a little bit of this when we were doing complex chemistry, because one of the things that we really focused on was the hexaaqua ion. Now, just whilst I'm there, now that we've got a bit of a base definition of what we're going to be looking at today and over the next coming weeks, I want to then focus on, let's first of all box off all the metals that you're expected to now learn about. And this, when I say learn, you're going to need to learn a string of colors for each of these metals. So you can put metals to learn, metals to know. Okay, first one, chromium. Second one, manganese. Third one, copper. Fourth one, cobalt. Fifth one, aluminium. Sixth one, zinc. And iron 2, iron 3, so iron, and iron 2. I feel like I'm missing one. Chromium, copper, iron. Yeah, because it's just iron and iron 2. I believe that's all of them. Yeah, so 7, I believe. Oh, do you know what? Suddenly realized we can check. There. 1, 2, 3, 4, 5, 6, 7, 8. Ah, I'm missing nickel. Nickel. So it's actually, you can add charges to these. Now, I actually don't think that's particularly fair. They talk about the fact that you need to know MB, wrong account, vanadium. Oh yeah, you need vanadium as well, add vanadium. Oh, vanadium. Absolutely, you need vanadium. So essentially what I'm gonna do is, I'm gonna do a lesson on each one of these and just add bits of detail on that you're just gonna have to learn about. I've already taught you vanadium, that's already done. You need to know that vanadium can have 5 different colors, but actually it's 4 different colors, but one's a mixture, which is going to be yellow, green, blue, green, violet. Yellow, green, blue, green, violet. Yeah, 5, 4, 3, 2, 1. Or hang on, 5, 4, 3, 2, and stops. Lol. So we've already done vanadium. But these are the metals that you guys have got to know. So now that we've kind of got the list of metals that we're going to learn about, what we need to now do, I just want to talk to you about what this means in terms of being in water. Okay, so transition metal compounds, are often white as anhydrous. That means without water. Yeah, as anhydrous solids. Okay, so for an example, we're going to start work on one particular metal today. We're going to be mentioning acidity about these. So I'm just going to talk to you about copper, because you guys know copper well. So copper. So the example now, of course, of copper is copper sulfate. You guys know this stuff well. There are 2 versions of copper. We've got the anhydrous. Yeah, so anhydrous copper sulfate. And this is white. Anhydrous copper sulfate. And this is white, which is the sentence above. Yeah, so this is our white compound. And then we've got our hydrated. So we've got hydrated copper sulfate. And that's blue. Okay, and that's a bright blue. There you go, dark blue. Right, so what we now need to do is we need to talk about the process. So what we're going to do is, I'm actually going to take the copper sulfate white solid, going to take our white solid, and I'm going to add it to some water. Yeah, we're going to add it to some water. Now, we know what immediately is going to happen. The copper sulfate is going to dissolve, and this is where everything now begins. Everything starts off hexaaqua ion. Hexaaqua ions. So we're going to form hexaaqua copper 2, hexaaqua copper 2 complex. Everything starts off hexaaqua. Let's now make it 3D. Water, 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 and water. I like it. I'm going to add in my H's. I'm going to be really good today. Right. So when they first added transition metal compounds to water, they had an expectation. Everything starts off hexaaqua. It's a good rule, that everything starts hexaaqua. Love that. Everything starts hexaaqua. So the first thing we need to talk about today, and it's funny that I've done, so first thing is know your metals. Second thing, just recapping the hexaaqua ion, the octahedral complex, 6 waters. Now I'm not going to do the reactions in aqueous. What we're going to do is talk about the acidity. Understand acidity. So, change a learning objective. Change my mind. Don't like it. Not having a good day today. Okay, so The first observation is, so if you add, so strange observations. When sodium chloride is added to water, the pH remains unchanged. Standard, it was thought that most salts would have little to no effect on pH. Now, if you've been doing acid base with me, you'll know that conjugate salts do have a pH of kind of like a 9-ish. Yeah, in terms of like if you've got the conjugate base, but if you've got the conjugate acid, you're going to have a pH of something like, I don't know, 5, 6, somewhere around there. So they are, like, you do have salts which are slightly acidic and slightly basic. However, when you have copper sulfate, so expectation, transition metal salts would have little to no effect on pH. That was the expectation. It turned out not to be true. Observation, real life observation. Okay, so what they actually observed was something they really didn't expect. So you add observation, adding small amounts of copper 2 sulfate to water, the pH drops quickly to pH 5. Now, that was a very odd observation. You keep adding it, by the way, it'll keep dropping. But we like to talk about a 1 molar solution being about pH 5. Now, that was a significant drop. That observation told us that transition metal salts are acidic, and they didn't know why. Now, just to let you know, that observation, addition, adding small amounts, second observation, small amounts of iron 3 chloride to water, the pH drops quickly to 3. Now that is very acidic. Now this was a very odd observation. They were very confused by this. They didn't really understand where the acidity was coming from. Now, this actually provides us these observations, which we would have done in class, by the way, but we can't, obviously. So what I now need you guys to make the notes about, now this is the important bit. This is the observation that you guys need. So it's not letting me zoom out. Metal 2+ ions, M2+, pH 5. Metal 3+ is pH 3. You guys need that. Common questions. Suggest a pH of iron 3 chloride at 1 mole per dm cubed, 3. Yeah, they'll give you metals that you've never seen before. Doesn't make any difference. You can apply a rough rule of pH to the transition metal charges. Now, what they had to do is we now have to explain this. Okay, so here's what's happening. Subheading, acidity. TM acidity. When TM salts dissolve, the transition metal, the TM ion, will form the hexaaqua ion. It will immediately coordinately bind to water, will immediately form the hexaaqua ion. So here's what it looks like. White copper sulfate, anhydrous, add to water. Add to water. And I immediately form the hexaaqua ion. Now the hexaaqua, I'm just going to do the waters as circles today. There we go. We form the hexa. Those little blobs, I'll do a key. Yeah. There we go. So it forms the hexaaqua ion. The sulfate ions, meh, don't really care about. Doesn't really do much. Yeah. But the copper immediately forms the hexaaqua ion. Now, so why would this make the solution acidic? What we now need to do is we need to have a look. At what's happening with the waters. Right. So here's what's happening. The central core, the transition metal ion at the center. So I've got Cu2 plus here. What is happening is it's binding coordinately to the H2O. Now, let's look at this in like a series of steps. So the water molecule previously was over here, and the water molecule was already polar. This is why it's attracted to it in the first place. And it has 2 lone pairs of electrons. Now what happens is this will bind coordinately to the metal ion. This is because, why can it do this? Why do TM ions form complexes? Form complexes, question mark. Answer, we'll do in red. High charge density. High charge density can attract ligand close enough to form dative bond. High charge density. So when the water molecule binds to it, so that's stage 1, that's step 1 now. Yeah, so what does step 2 look like? So let's now just change the color and do step 2. I'm just gonna then switch this over to dark green. So here's step 2. The dative bond has been made. I think I should make this thicker. The dative bond is made. Now what's happened is one of the lone pairs, the other lone pair is facing now in the other direction, like that if you wish. Yeah, but once these electrons have bound, notice how close they were in the original. This is the original pair of electrons. It is owned very clearly by the oxygen. Now they've been pulled down to form a dative covalent bond. Now what that means is, if you pull electrons in the molecule this way, on forming that dative, the electrons in the OH bonds, which were previously around about here, bit towards the oxygen, 'tis polar, yeah, now become down here. The bonds become much more polarized. Yeah. So we say OH bond in water becomes more polar. Now, why would it do that? Due to high charge density, everything comes down to charge density. High charge density of metal ion. Right, what effect is this going to have to the bond strength? This decreases OH bond strength. More can break off. H plus can break free. Right, and this is where the acidity comes from. Because what we now, this is the third step. Third step is that the water molecules will actually, the electrons will hop back that way and H plus will break off. And the O is then left as a negative. So the OH can actually break free and form, and that's where the pH comes from. Now, this explanation also, I want to put my circle back. This actually explains the difference in pH between the different ion charges. Because if you were to take that +3, here's the comparison. Let's do a comparison. Two plus, 3 plus. Number one, the 2 pluses tend to be larger than the 3 pluses. They tend to be bigger. Every time that you increase charge on somebody, its size decreases. Hence, so it's even more charge dense at the 3 plus. So here's the difference. So we've now got a water molecule bound dative covalently, and the 2 plus pulls the electrons down here to make these more polar, and they become weaker. H plus can break free. pH 5. But now we've got a 3 plus ion, which is even more charge dense. Yeah, what that means is the electrons are pulled way down towards the +3, increasing the polarity even more can break free. pH 3. Increased charge density leads to increased polarity of the OH bond, weakening the OH bond, more break free. So this explains why the pH of transition metal solutions is below 7. Now, do you know what? I'm actually going to leave today's lesson at that point. I just wanted to explain the acidity of them, and then I'm actually going to pick this up next lesson. There's no point in me going any further at this point, because I'm going to then start work on single metals at the next lesson. So I'm going to, that's if I can even make my laptop do what I'm asking it to do, which I can't. That one there. Right, guys, I'm going to leave you there today. I'll send you some questions over regarding acidity, just to show you how common these questions are, and I will see you guys on. I'll see you guys soon next lesson. See you later, guys.